Okay, so here we have to cheat a little bit and look up the volume formula for n-dimensional spheres. And it turns out in even dimensions, the volume formula is pretty easy. In odd dimensions, it's actually not that hard either, but in even dimensions, like 2 dimensions, 4 dimensions, 6 dimensions, 8 dimensions, the formula is actually pretty easy. So we're only going to look in even dimensions. So that's why I say we're cheating a little bit. So in a 2k dimensional sphere has volume pi to the k over k factorial. So a 2-dimensional sphere, k would be 1, right? The 2-dimensional sphere is just our regular old circle, right? That's in 2 dimensions.
Yep.
So pi to the k, remember k is 1, pi to the 1 over 1.
So
the volume, the area of a circle is
pi.
Just like we thought. In 4 dimensions, k would be what in 4 dimensions?
2.
2. The volume is pi squared over 2.
We've seen that before.
Yeah, we have seen that before. In 10 dimensions, what is the volume of a 10-dimensional?
Well, it's pi to the 5th, over 120.
Yeah. Pi to the 5th over 120. Okay. Now, that's for radius 1. We have to do times the radius to the 2k power, because like in 2 dimensions, things scale as squared. 4 dimension, they scale as the 4th. So they'll scale as the radius to the power of the dimension. Okay? But we know what our radius is. Our radius is
1/2. It was the square root of n.
n, where n was the dimension, so that's the square root of 2k
minus 1
over 2. Okay? So the volume of our middle sphere has a very, very easy formula in even dimensions. Pi to the k over k factorial times the square root of 2k minus 1 over 2, the radius, to the 2k power.
And then this needs to be greater than 8.
Well, so let's be careful. Our big cube in 2k dimensions, what do we have to do? What are the side lengths?
They're all 2.
They're all 2, so we have to raise 2 to what power?
2 to the 2k.
2 to the 2k. This has to be greater than 2 to the 2k. Alright?
Alright, here it looks like we could take the k root of everything. No.
Well, the
We don't have
problem
a
is
k.
the k factorial. You're almost right. We have to take the kth root of k factorial.
But that's complicated.
That is complicated, but we can still play around with this a little bit. We can still play around with this just a little tiny bit. Okay?
Okay.
Alright, so let's see what happens here. I got the square root of 2k minus 1.
2k. Mm-hmm.
Okay? Maybe to simplify, well, no, we can leave it like this because we're gonna do this on
Wolfram Alpha?
on Mathematica. On the bottom, I have a 2 to the 2k power. I have a 2 to the 2k over here, and I can divide. Okay, so on the bottom, I've got, if I want to divide everything by 2 to the 2k, I already have a 2 to the 2k over here, so they multiply. So I get 2 to the 2k times 2 to the 2k. Do you know what this is?
2 to the 4k.
Yeah, 2 to the 4k, or 4 to the 2k. Okay. So I'm left with an interesting expression, pi to the k over k factorial times 4 to the 2k times square root of 2k minus 1 to the 2k.
And then this side?
This has to be greater than 1 because I divided by that side.
Mm-hmm.
Okay.
Very simple.
Sorry for being mushy with this. I want to put 4 to the 2k in terms of to the power of k. All right, so that's 4 squared to the k. So this is
16 to the k.
right. So this ends up being pi over 16 to the k times 1 over k factorial. That's that.
Mm-hmm.
Times the square root of 2k minus 1 to the 2k. And we're wondering if this is ever bigger than 1. Okay, now this is very hard to evaluate. So we're going to go
Mathematica.
we're going to go to mathematic. And remember, k is half the dimension. We're in dimension 2k here. So whatever k we solve for, we got to multiply by 2 to see when our internal sphere is bigger than the big sphere. All right, you ready to go give it a try?
Yeah.
All right, let's do it.